Hello and welcome to this video. We'll see an example of using Mohr circle to transform stresses on a 2D stress block, knowing the angle of orientation here. So we're given the top right corner of the screen. You see that we have a stress block with 3 KSI compressive stress in the y direction, 7 KSI tensile stress in the x direction, and a positive shear stress of 4 KSI. And it's an example we solved before. We solved it from the point of constructing Mohr circle, but in this example here we'll see how to use that Mohr circle to figure out the stresses for the other block that's shown below the first one with a 15 degrees orientation clockwise. So that's the same Mohr circle we constructed in the previous video. And we want to see the values for sigma x prime, sigma y prime, and tau x prime, y prime at 15 degrees angle clockwise. So the first thing you do is you represent the given stress block and in the Mohr circle here as a diameter in the Mohr circle. And you do that by plotting the 2 points of sigma x and negative tau xy and sigma y tau xy. And if you connect between these 2 points on the circle, that's the diameter representing that block, which I'm referring to here as the purple and purple color. And then we're thinking about that 15 degrees here for the orientation of the new stress is in real life, is in real life 15 degrees, but in Mohr circle it's double that, as we explained in the previous video. And now that will bring us to a different diameter, so the diameter will rotate from the purple 30 degrees now clockwise, and that will be the diameter representing the new orientation and transformed stresses here. Sigma x prime, tau x prime, y prime, and sigma y prime. And if we take out these triangles here, so we have this big triangle here that refers to half of the diameter or the radius here from the point of sigma average, which is 2 here, average of negative 3 and 7. Let's see, so that's in sigma average, and the radius here, I will refer to the angle between this radius and the horizontal axis as alpha. And you see here the bottom point is referring to sigma x prime, negative tau x prime, y prime. The difference, horizontal distance of that triangle here is the difference between the coordinate of sigma x prime and the coordinate of sigma average. So if I want to find sigma x prime and tau x prime, so basically the base of this triangle and the height of this triangle, I will have to figure out first what's alpha, the angle here. So to figure out alpha, I have to deal with another triangle, which is the triangle that is given to us, that connects between sigma average and sigma x and negative tau xy. And I will be able to calculate the angle of that with the horizontal axis, which we used to call the 2 theta principle, the angle to the principal stresses. And if I know 2 theta principle, and I know that there's a 30-degree angle between the given stresses and the transformed stresses, then alpha will equal to 30 degrees plus 2 theta p. So now it becomes a problem of finding 2 theta p, and I will be able to find alpha, and using alpha I will be able to calculate the transformed stresses. So if I want to calculate 2 theta p, I will have to deal with this hatched triangle here, and it's equal to tan inverse of the height of this triangle, which is the coordinate of the tau xy, which is 4. And I'm dealing here with absolute value, divided by the base of the triangle, which is the difference between sigma x and sigma average, so 7 minus 2. So you end up with 38.7 degrees. So we have now 2 theta p. We'll be able to figure out alpha of the red triangle that we discussed before. So alpha will be 68.7 degrees. Now, knowing alpha, I will be able to calculate sigma x prime tau x prime, but before that, I will need to find the radius of the circle. And if you see on the top here, the radius is square root of the base and the height of the triangle to the power 2 each. So that's will give us 6.4, and the units here are in KSI. So I have R, I have alpha. I will be able now to focus back again on that triangle of the transform stresses, and I'll be able to calculate tau x prime y prime as the radius times sine alpha, and that will give us here tau x prime y prime to be 5.96 KSI. So that's the first one stress that I'm looking for, the shear stress. Next is sigma x prime, which is equal to sigma average plus r cosine alpha. So sigma average is basically where the head of the triangle, that point, left point of the base, and then I will add to it the distance between that point and the right side of the triangle, so that will be r cosine alpha. Then if I plug in the numbers, I will end up here with sigma x prime to be equal to 4.3 KSI. And then sigma y prime is not shown in this triangle, but it's actually similar to the formula of sigma x prime. But then here I'm changing the plus to be negative. So it will equal sigma average minus r cosine alpha. And I will find here it's equal to negative 0.325 KSI. So sigma y changed to be sigma y prime. So it changed from 3 compression to 0.325 compression. Sigma x changed to be tension 7 to be less value of 4.3, and the shear stress actually increased from 4 to still be a positive value of 5.96. So you can see here that usually when using Mohr circle to find transform stresses, you will have to find 2 theta p. Where is that original state of stresses is in the Mohr circle relative to the horizontal axis, which is 2 theta p. And then using the 2 theta p information, you will be able to figure out the right triangle to use its geometry to calculate the transform stresses. All right, I hope you enjoyed the video. See you in a future one, and take care.